Hello everyone, this is the second part of the video acid-base and functional group exchange reactions, and in this video I'm going to be looking specifically to nucleophilic substitutions. And as a reminder, this video is based on chapter 2 in Smith's organic synthesis, and you have a copy of this available through the Nobel database, and there is a link in the module Blackboard to the resource. So you can have two types of nucleophilic substitutions, and hopefully this sounds familiar from previous years, the second and first year modules. SN2, nucleophilic bimolecular nucleophilic substitution, and SN1, monomolecular nucleophilic substitution. In the SN2 mechanism, the nucleophile enters the molecule as the living group is leaving the molecule. So you have this intermediate of reaction. The kinetics of the reaction is an order too. It depends on the nucleophile, and it also depends on the compound you are doing the reaction on. And if you notice in this structure, if you have a chiral compound, you will end up with an inversion in the configuration of that chirality. The nucleophile the substituted product will have an inverted configuration in that chiral carbon with respect to the reagent, and that is because of how this intermediate of reaction works and where the nucleophile attacks and how the living group leaving the molecule. You have here a list of strength of nucleophiles from NH2 minus as a strong nucleophile to a perchlorate anion as a weak nucleophile. So some sort of reactivity series of how strong those nucleophiles are compared to each other. The reaction here is an interesting reaction on on an epoxide. Epoxides are very reactive. And for example, here, as you see, of the two carbons that the nucleophile can attack, it attacks preferentially the one that has less steric hindrance. It attacks the one that does not have the substituent. And you have this intermediate compound that then protonates to form the alcohol. In SN1s, this is a first reaction order, and it is called first reaction. It's a first reaction kinetic order, and that is because the kinetics depend not on the nucleophile but on the target molecule, the one that you are doing the substitution on, and it goes through via a carbocation. So the living group leaves first the molecule, and you form a carbocation, and then the nucleophile attacks the carbocation to form the final product. And you can have because you lose for a chiral compound, if you have a chiral carbon, you are losing, when you form the carbocation, you are losing the chirality, you're losing the fixed stereochemistry in that carbon. So you end up with a mixture of both possible chiral compounds, and how much you have one or the other depends a bit on the nature of the nucleophile and the living group. Because, for example, if you have an intermediate in which the living group it's sterically hindering the nucleophilic attack, then you end up with the nucleophile attacking on the opposite side to where the living group is, even if it has already left the molecule. While in other cases, if the steric hindrance of the living group is smaller, the nucleophile can attack from the same side of where the living group is. So in general, you do get racemic mixtures, but not necessarily in equal proportions. And sometimes you can have molecules, for example, when you're forming your carbocation in a cycle in which the structure, the chirality, the attack is determined just by the structure of the carbocation you are forming. So for example, in this compound, when you form the carbocation here, well, there is no way the bromine anion can attack anywhere but from here, so you end up with the bromine in the same position with the same chirality as the original leaving group. And you can have, because you're using carbocations, every time you have carbocations, you quite often have rearrangements. So for example, if you look at this compound, you could think initially this would be a carbocation that would form. However, that's the most unstable carbocation you can have in a primary carbocation. This one here is much more stable, so the substitution will not happen here on this carbon. It will happen, the chlorine atom will go to the carbon part of the ring, and that is because this intermediate of reaction of the two possible carbocations you can form, that one is the most stable one, so the one that will form. So how can you predict if you're going to a nucleophilic, you're going to have an SN1 or an SN2? Well, there are three things that will influence if you're going to have an SN1 mechanism, carbocation, or an SN2 mechanism, a combined nucleophile entering the molecule while the leaving group is leaving the molecule at the same time. And that's the nature of the leaving group, the nature of the nucleophile, and the solvent in which you are conducting the reaction. So the leaving group. When you have a leaving group attached to a methyl group or a primary carbon, typically an SN2 mechanism is favored. And that is because the carbocation you would be forming if you have a primary carbon would be too high energy, would be too unstable, and thus unlikely to form. If you have a leaving group which is attached to a tertiary or an allylic or a benzylic carbon, something that will stabilize that carbocation intermediate, then that carbocation will be relatively stable, and that will favor an SN1 mechanism, just because you are forming an intermediate of reaction that is more stable, more likely to form. Another aspect that is going to influence whether you're going to have an SN1 or an SN2 mechanism is the nucleophile. A strong nucleophile, a powerful nucleophile, for example, one that has a negative charge, will favor the SN2 mechanism, while a weak nucleophile, something like water or alcohols, will favor as SN1 mechanism, the carbocation mechanism. And finally, the solvent. When you have aprotic solvents that are polar, will favor an SN2 mechanism because they enhance the reactivity of your nucleophile. However, if you have polar protic solvents, then that will favor, for example, water could be a polar protic solvent. You would favor the SN2 mechanism because it stabilizes the carbocation intermediate. So this is just a table that compares SN1 and SN2 in terms of the kinetics of reaction, first order and second order. How important is the nature of the leaving group is important in both cases, and the reactivity for halogens, which is a typical leaving group, is the same for all of them. Iodine is a better leaving group than bromine, a better leaving group than chlorine, and fluorine as a final in the chain. The nature of the nucleophile is particularly important in an SN2 reaction because it is part of the, it is going to be part of the kinetics of the reaction. The preferred solvent for an SN1 reaction is a polar protic solvent, and for an SN2 a polar aprotic solvent. And in general, for stereochemistry, you have if you have a chiral, if your carbon, the carbon where you're doing the substitution reaction is a chiral carbon, then you have an inversion of the stereochemistry for an SN2 reaction, and some mixture of racemization with sometimes one of the stereoisomers as a favor one in the SN2 reaction. And it is rare to have a rearrangement in the structure in an SN2 reaction, just because, well, that's not in the nature of how the reaction is. However, in SN1 reactions, rearrangements, because of that, the stability of the carbocation and the possibility of forming a more stable carbocation once the reaction has started, are common. So this is the end of this part of the video dedicated to nucleophilic substitutions. Thank you for watching, and I hope it was useful.